On behalf of James and myself, I would like to thank the organisers for the opportunity to speak at this wonderful conference. I am sorry that I cannot be with you in person. For many years, I've been working towards making Sydney Analytical an international leader for scientific analysis of cultural heritage objects and materials. The projects that I've been honoured to be involved with has helped to open new areas of research for university-based collections, creating new opportunities for interdisciplinary collaborative research across multiple faculties on campus and with external partners from Australia and overseas. This has included the development of numerous collaborative projects with the Chowchak Wing Museum, the Rare Book and Special Collections Library at the University of Sydney, and the Department of Archaeology. I'd like to present some of our exciting work in the... Before I go any further, I would like to acknowledge and pay my respects to the traditional owners of the land, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the Camperdown campus of the University of Sydney is built. As we share our knowledge, teaching, learning and research practices within this university, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. X-ray fluorescence spectroscopy is a ubiquitous tool in the analysis of cultural heritage objects and materials and is commonly used as a first-pass tool for gaining an elemental understanding of the material composition. Instrumental advances in portability, affordability, sensitivity, and improved detection limits have given rise to the widespread use of portable XRF units in conservation laboratories, in the field, in remote locations, and archaeological sites globally. However, rarely does any analytical tool provide all the answers, and it is important to understand the possibilities and limitations of this technique. This slide provides an example where other analytical techniques can be employed to provide complementary information. In the XRF example on the left-hand side of the screen, we have spectra of realga and orpiment, displaying peaks attributable to arsenic and sulfur. Orpiment, due to its golden colour, was used in ancient times as a pigment and dye, while realga was a common red pigment for paints and dyes. It is not possible with only XRF data to make an identification. On the right-hand side of the slide is illustrated the Raman spectra collected from realga, pararealga, and orpiment. As you can see, they look very different. Although all three pigments contain both arsenic and sulfur, the number of atoms and their arrangement in space, that is their molecular structure, are very different. On the previous slide, I spoke briefly about Raman spectroscopy. Together with infrared spectroscopy, they are referred to as vibrational spectroscopy, with both techniques measuring the amount of energy it takes for a molecular vibration to occur. This provides information about the chemical composition and molecular structure of the sample under investigation. The samples analysed can come in many different shapes, sizes and colours. The graphic on this slide illustrates the diversity of sample types that have been analysed in our facility. These techniques are widely used because they are non-destructive, in some instances non-contact, little to no sample preparation is required, and in situ analysis is possible. In addition, there is a range of instrumentation that allows for analysis from the microscopic level through to the macroscopic. Sydney Analytical houses more than 30 high-end instruments, many of which are the most advanced of their kind in Australia, some of which are shown on this slide. Our range of instrumentation covers not only laboratory-based equipment, but also portable instruments. On this slide, you can see the range of portable equipment, infrared, Raman, and XRF systems that can be used in the laboratory, at a museum, or in the field. In fact, all of these instruments are being used outside the laboratory environment on a regular basis. I'd briefly like to share with you some of the research that Sydney Analytical have been involved with in collaboration with our colleagues at the Chowchak Wing Museum at the University of Sydney. In the middle of this slide is an image showing the interior and exterior of the cedar coffin of the woman Merenethetis, purchased in 1858 by Sir Charles Nicholson, who donated it to the University of Sydney as a foundation piece for the Nicholson Museum. Although previously thought to be empty, the coffin was found to contain the heavily disturbed remains of a mummy, torn apart by tomb robbers looking for amulets and jewels. The mixed contents included bandages, bones, beads, and resin. It is highly unusual for complete but disturbed mummies to survive in museum collections, as museums have historically sought complete mummies for display. Most extant mummies are thus well preserved specimens with undisturbed bandages. Consequently, scientific investigation of mummies is usually limited to non-invasive and non-destructive techniques. The mixed remains within the Maranatha's coffin therefore presented a unique opportunity to conduct a comprehensive suite of scientific analyses of a mummified individual. A collaborative project commenced in 2017 between the University of Sydney's Nicholson Museum, at the time, which then became the Chowchak Wing Museum, Sydney Analytical, Macquarie University, and the University of Newcastle. Raman, infrared, XRF, and other complementary analyses were undertaken to investigate the various objects excavated from the coffin in 2018. These techniques, along with digital image manipulation, were employed in an attempt to determine the chemical composition of the faded hieroglyph pigments in order to produce a digital model of the coffin. The front surface of this Australian Aboriginal shield, collected by J. Boyd in about 1888 and forms part of the Macleay collection, is decorated with red, brown, and blue pigments arranged into a square pattern across its face. There is significant wear and tear, indicating that this was likely used by its maker or owner before it was collected by Boyd. The shield is thought to have been painted with a mixture of natural brown and red ochres, black, usually sourced from charcoal, and a vibrant blue pigment. The blue pigment was identified by Raman spectroscopy as ultramarine blue, but it was not determined whether it was synthetic, possibly Reckitt's blue, or natural ultramarine, lazurite, the main mineral component of lapis lazuli. Lapis lazuli is typically identified using either optical or scanning electron microscopy, since its morphology and particle size is distinct from the uniform, small, and rounded particles of the synthetic ultramarine blue pigment. We are re-examining the blue pigment together with other available samples to establish its origin. Many of the research projects that are undertaken at Sydney Analytical are collaborative. Where possible, we enjoy the challenge of developing new methodologies. In 2017, after meeting Lucilla Ronai from the Australian National Maritime Museum at a conference, we discussed the problem of how we could identify and distinguish between cellulose nitrate and cellulose acetate reliably, rapidly, and non-destructively. Cellulose nitrate, transparent plastic film, was used by photographers and movie filmmakers from its release in the 1880s to the 1950s. The storage of this material is a challenge for cultural institutions because of its instability and hazardous nature, as nitrate is highly flammable and deteriorates over time. Historically, cellulose acetate gradually began to replace cellulose nitrate as it is not flammable. Despite its non-flammable properties, leading to cellulose acetate being called safety film, over time it became clear that it also deteriorates in hazardous ways. Identification of cellulose nitrate and cellulose acetate in collections is necessary for preservation and risk management to collections and humans. At the time of this work, there was no single identification method readily available to heritage institutions that met the requirements to identify and distinguish between cellulose nitrate and cellulose acetate. In this study, samples from both the Sydney University Museums and Australian National Maritime Museum collections were analysed using infrared total reflection spectroscopy. Since the paper has been published, numerous institutions worldwide have used this methodology to characterise their often immense collections of cellulose-based films. In 2018, Maki and colleagues published a method for analysing bone diagenesis using vibrational spectroscopy. Diagenesis is a critical process for understanding the taphonomy of archaeological vertebrate bone assemblages particularly those diogenic properties relating to heat exposure. The temperature and heating environment that led to a bone specimen being charred, cracked, polished, or calcined can reveal much about the cooking preference of past people. For example, it may reveal whether a cut of meat was boiled, roasted, or cooked over an open fire, and the amount of heat that it was exposed to. The research undertaken by Marquis and colleagues determined that the most significant spectral differences were observed between 700 and 800 degrees Celsius and included degradation of the organic protein component, as well as the presence of new bands attributable to the inorganic matrix, as seen in the schematic representation in the figure on the bottom right-hand side of this slide. These biomarkers have been used by our own team to investigate both an experimental sample of animal bones from common domesticates, sheep, cow, and pigs, and archaeological samples from a late 19th, early 20th century assemblage excavated in the southeast of Tasmania. Our project moves beyond the experimental research performed in a controlled laboratory to test the efficacy of vibrational spectroscopy on archaeological artefacts subjected to post-depositional processes in the ground for 100 years or more using portable instrumentation. This first figure presents the ATR spectra collected using a portable FTIR spectrometer from 3 samples of animal bones subjected to 400, 700, and 975 degrees Celsius. The next 2 figures are an expansion of these spectral regions. The bands marked on the figures at 3,570 and 630 wave numbers are assigned to the hydroxyl stretching and libation modes, which are attributed to a heat-induced reorganization of bioapatite's microcrystalline structure. Other noticeable changes are the decreased intensity of the spectral region from 1700 to 1350 wave numbers, assigned to a range of components including proteins, lipids, and carbonates. The decrease in the intensity of these features is a result of the destruction of the organic matrix, with the removal of lipids, degradation of proteins, and change in carbonate bands reflecting the change in the bone's inorganic matrix. These observations concur with those collected with laboratory instruments, confirming the transferable nature of this method. This slide presents the FTIR-ATR data collected from a range of archaeological material. Examination of the spectra collected from samples in C and E reveal the presence of bands at 3,570 and 630 wave numbers, marked by the asterisks, indicating that these samples were subjected to temperatures of at least 700 degrees Celsius. In spectrum A, there are 2 bands at 2,919 and 2,849 wave numbers, which are CH stretching bands assigned to lipids and proteins. The AMOD 1 and 2 bands are due to the presence of organic material. These bands were not present in the sample burnt at 400 degrees Celsius. However, Marquis reported these bands were present in samples subjected to temperatures below 700 degrees. The oven that was used to burn the samples had some issues with the thermostat. Future work will require a reliable furnace. Regardless of these problems, this work has demonstrated the usefulness of portable infrared spectroscopy for ascertaining the burning temperature. In addition to portable infrared spectroscopy, similar data were collected using a handheld Raman system. The data from the reference samples are provided on the left-hand side and the archaeological material on the right-hand side. The spectral quality for the data collected from the samples at 400 and 700 degrees Celsius is very poor, and this is attributed to the fluorescence of the organic material within the bone, and it was a phenomenon that was also observed by Marquis. The spectrum from the sample burnt at 975 degrees Celsius is of good quality with a high signal-to-noise ratio. It is a much simpler spectrum compared to its infrared counterpart, and the bands are attributable to the inorganic matrix. The quality of the data from the archaeological material is highly variable. The Bravo Raman spectrometer has a built-in fluorescence mitigation algorithm, but it wasn't able to completely counter the effects of fluorescence, as can be seen in spectra C, F, G, H, and I. Collecting Raman data can sometimes be very difficult if the sample is moving or not in focus, which is potentially why there is only noise in the first two spectra. The features that are marked at 779, 584, and 407 Raman shift are very broad and are potentially spectral artifacts. In the future, more work will be required to develop the application of this methodology. There are many people who have been involved in the projects which I have shared with you today. Their names are on this acknowledgement slide. I thank you kindly for your time.